Projective Geometry, Volume 1, by Oswald, Veblen, and John Wesley Young.
Chapter 9, Geometric Constructions, Invariants. Section 83, The Degree of a Geometric Problem. The specification of a line by two of its points may be regarded as a geometric operation. The plain dual of this operation is the specification of a point by two lines. In space, we have hitherto made use of the following geometric operations. The specification of a line by two planes. This is the space dual of the first operation mentioned above. The specification of a plane by two intersecting lines, the space dual of the second operation above. The specification of a plane by three of its points, or by a point and a line. The specification of a point by three planes, or by a plane and a line. Footnote: an operation on one or more elements is defined as a correspondence whereby to the set of a given elements corresponds an element of some sort, chiefly section 48. If the latter element is uniquely defined by the set of given elements, in general, the order of the given elements is an essential factor in this determination, the operation is said to be one-valued. The operation referred to in the text is then a one-valued operation defined for any two distinct points and associated with any such pair. The order of the points is in this case immaterial, a new element, namely a line. These operations are known as linear operations or operations of the first degree, and the elements determined by them from a set of given elements are said to be obtained by linear constructions or by constructions of the first degree. The reason for this terminology is found in the corresponding analytic formulations. Indeed, it is at once clear that each of the two linear operations in a plane corresponds analytically to the solution of a pair of linear equations, and the linear operations in space clearly correspond to the solution of systems of three equations, each of the first degree. Any problem which can be solved by a finite sequence of linear constructions is said to be a linear problem or a problem of the first degree. Any such problem has, if determinate, one and only one solution. In the usual representation of the ordinary real projective geometry in a plane by means of points and lines drawn, let us say, with a pencil on a sheet of paper, the linear constructions are evidently those that can be carried out by the use of a straight edge alone. There is no familiar mechanical device for drawing lines and planes in space, but a picture, which is the section of a plane of a projection from a point, of the lines and points of intersection of linearly constructed planes may be constructed with a straight edge, chiefly the definition of a plane. As examples of linear problems, we mention a. The determination of the point homologous to a given point in a projectivity on a line of which three pairs of homologous points are given. B. The determination of the sixth point of a quadrangular set of which 5 points are given. C. The determination of the second double point of a projectivity on a line of which one double point and 2 pairs of homologous points are given. This is equivalent to B. D. The determination of the second point of intersection of a line with a conic, 1 point of intersection and 4 other points of the conic being given, etc. The analytic relations existing between geometric elements offer a convenient means of classifying geometric problems. Confining ourselves, for the sake of brevity, to problems in a plane, a geometric problem consists in constructing certain points, lines, etc., which bear given relations to a certain set of points, lines, etc., which are supposed given in advance. In fact, we may suppose that the elements sought are points only. For if a line is to be determined, it is sufficient to determine 2 points of this line. Or, if a conic is sought, it is sufficient to determine 5 points of this conic, etc. Similar considerations may also be applied to the given elements of the problem, to the effect that we may assume these given elements all to be points. This merely involves replacing any given elements that are not points by certain sets of points having the property of uniquely determining these elements. Confining our discussion to problems in which this is possible, any geometric problem may be reduced to one or more problems of the following form. Given in a plane a certain finite number of points, to construct a point which shall bear to the given points certain given relations. Footnote: the remainder of this section follows closely the discussion given in Castelnuovo, Lezioni di Geometria, Rome, Milan, Volume 1, 1904, pages 467 forward. In the analytic formulation of such a problem, the given points are supposed to be determined by their coordinates, homogeneous or nonhomogeneous, referred to a certain frame of reference. The vertices of this frame of reference are either points contained among the given points, or some or all of them are additional points which we suppose added to the given points. The set of all given points then gives rise to a certain set of coordinates, which we will denote by 1, a, b, c, ... and which are supposed known. Footnote: in case homogeneous coordinates are used, a, b, c, ... denote the mutual ratios of the coordinates of the given elements. These numbers, together with all numbers obtained from them by a finite number of rational operations, constitute a set of numbers, k equal the set 1, a, b, c, ... which we will call the domain of rationality defined by the data. Footnote: a moment's consideration will show that the points whose coordinates are numbers of this domain are points obtainable from the data by linear constructions. Geometrically, any domain of rationality on a line may be defined as any class of points on a line which is closed under harmonic constructions, i.e. such that if A, B, C are any three points of this class, the harmonic conjugate of A with respect to B and C is a point of the class. In addition to the coordinates of the known points, which, for the sake of simplicity, we will suppose given in non-homogeneous form, the coordinates x, y of the points sought must be considered. The conditions of the problem then lead to certain analytic relations which these coordinates x, y, and a, b, c, ... must satisfy. Eliminating one of the variables, say y, we obtain two equations. f1 of x equals 0, f2 of x, y equals 0. The first containing x but not y, the second, in general, containing both x and y. The problem is thus replaced by two problems, the first depending on the solution of f1 of x equals 0 to determine the abscissa of the unknown point, the second to determine the ordinate, assuming the abscissa to be known. In view of this fact, we may confine ourselves to the discussion of the problems depending on a single equation with one unknown. Such problems may be classified according to the equation to which they give rise. A problem is said to be algebraic if the equation on which its solution depends is algebraic, i.e., if this equation can be put in the form 1 x to the nth power plus a1 x to the n minus 1 plus a2 x to the n minus 2 plus ... plus a sub n equals 0, in which the coefficients a sub 1, a sub 2, ... a sub n are numbers of the domain of rationality defined by the data. Any problem which is not algebraic is said to be transcendental. Algebraic problems, which alone will be considered, may in turn be classified according to the degree n of the equation on which their solutions depend. We have thus problems of the first degree, already referred to, depending merely on the solution of an equation of the first degree, problems of the second degree depending on the solution of an equation of the second degree, etc. Account must, however, be taken of the fact that equation 1 may be reducible within the domain K. In other words, that the left member of this equation may be the product of two or more polynomials whose coefficients are numbers of K. In fact, let us suppose, for example, that this equation may be written in the form phi1 of x dot phi2 of x equals 0, where phi1, phi2 are two polynomials of the kind indicated and of degree n1 and n2 respectively, n1 plus n2 equal to n. Equation 1 is then equivalent to the two equations phi1 of x equals 0, phi2 of x equals 0. Then either it happens that one of these equations, for example the first, furnishes all the solutions of the given problem, in which case phi sub 1 being assumed irreducible in K, the problem is not of degree n, but of degree n1 less than n. Or both equations furnish solutions of the problem, in which case phi2 also being assumed irreducible in K, the problem reduces to two problems, one of degree n1 and one of degree n2. In speaking of a problem of the nth degree, we will always therefore assume that the associated equation of degree n is irreducible in the domain of rationality defined by the data. Moreover, we have tacitly assumed throughout this discussion that equation 1 has a root. We shall see presently that this assumption can always be satisfied by the introduction, if necessary, of so-called improper elements. It is important to note, however, since our assumptions A, E, P do not in any way limit the field of numbers to which the coordinates of all elements of our space belong, and since equations of degree greater than 1 do not always have a root in a given field when the coefficients of the equation belong to this field, there exist spaces in which problems of degree higher than the first may have no solutions. Thus, in the ordinary real projective geometry, a problem of the second degree will have a real solution only if the quadratic equation on which it depends has a real root. The example of a problem of the second degree given in the next section will serve to illustrate the general discussion given above.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.